This is the fourth and last lesson for Chapter 5. And before we get into the main topic, power, let's take a look at this asteroid impact. It might have been a meteor, not positive. In any case, this event took place in 1907, according to your book, 1908, according to other sources. And this gigantic object of some 50 to 60 meters across, as it entered the Earth's atmosphere, began to heat up and got so hot that eventually the stress forces from all of that heat internally caused it to explode several miles above eastern Siberia. And that's, if you're going to have an explosion like that, that's a good place to have it because hardly anybody lived there at the time. But this explosion produced an awful lot of energy and left behind an awful lot of debris, so the mass of the Earth, in a sense, increased. It was probably traveling at a speed, maybe 40 to 60,000 meters per second. And when it blew up above the Earth, it produced a wave that knocked down over 80 million trees by our best estimates over a area of about 830 square miles. Just as a point of reference, St. Louis County is 500 square miles. So if it would have hit down, just west of the Arch in the center of the St. Louis metropolitan area, it would have wiped out the entire St. Louis County, north, south, east, west, and city, and even across the river into East St. Louis. Imagine if it would have hit a major city. It also explains why there was no impact crater there, because it did not actually strike the Earth. In any case, that's a good example of the fact that our Earth has been hit by asteroids and meteors before. Most of the time, the meteors are very, very small, just fragments left over once they get into the atmosphere. And you might wonder, why does our Earth not look like the surface of the moon in terms of craters all over the place from impacts? And the reason, number one, is because we have an atmosphere that a lot of this stuff burns up in. But another reason is because of the moon itself, as well as the large giants of Jupiter and Saturn and Neptune. They are massive enough, and the moon is close enough that it kind of takes the brunt of all of these impacts so that we don't. Once again, we should know that God's looking out for us. He's designed this planet to be in the best possible place in our solar system. And a lot of parameters have to be just right for there not just to be any kind of life, but intelligent life, such as ourselves. And in order to protect that life, you can't be having these terribly destructive events taking place all the time. Now, that we do know there was one event, and by some estimates, this was an event that struck the Yucatan Peninsula area and produced so much debris in the atmosphere, it blocked off the sun, which took away basically the food supply, and all of your many of your major critters at the time, the dinosaurs, could not survive and went extinct. And part of the evidence we have for this is around that Yucatan Peninsula, underground, is some residual iridium, which is an element that is often found in meteors and extraterrestrial objects that strike planets. So that's some evidence. All right, let's get on to the main topic of this last lesson. And the main topic has to do with power. And once again, like with work, like with energy, like with force, we have the everyday kind of use of the word and meanings of the word. And then we have the much more highly specific definition of the word that we use in science. And of course, it's got to be highly specific if you're going to have a mathematical equation to go with it. And that's why this equation right here, the definition of power, is one that I would suggest you memorize. It would be given to you on the AP. I don't know if I give it to you on one of my tests because it's definitions and I don't generally give you definitions. But power is the work that is done in a period of time. And a good way to illustrate this is to imagine you're at the bottom of the stairs and just outside the physics classroom. Now you can walk slowly up those stairs, those 2 flights of stairs, or you can run up those 2 flights of stairs. I don't know how many stairs there are. I know that the grand entry, I believe there's 24. Don't ask me why I count them. But you can, if you walk up to the top or you run up to the top, you've done the same amount of work, because that work would be force, and this force would be the force of lifting your weight. This would be the weight of your body times your net distance, which would be the distance from the floor on the floor on the first level to the floor on the second level. But you'll notice that if you do it faster because you're running up the stairs, your delta T is smaller. And when your denomination gets smaller, your power gets bigger. So it takes more power to run up the stairs than it takes to walk up the stairs. Now, if you recall that work equals force times distance, and we'll use delta x here for distance. Now we have power equals force times delta x over delta t. And you should notice that delta x over delta t is velocity. So this is a very helpful equation, that power equals force times velocity. And again, these have to be in the same direction. And this equation you would not be expected to memorize, but it would be given to you on my test as well as on the AP test. Power equals force times velocity. Now you can talk about instantaneous power, and you can also talk about average power. In any case, the unit for power, if we were to break this down, would be the Newton times the meter per second. And if you remember a Newton, which is the unit for force, and force equals mass times acceleration, that means a Newton is a kilogram meter per second squared times velocity, which is meters per second. And so the units of power become a kilogram meters squared per second cubed. And nobody wants to talk about the units of power being kilogram meters squared per second cubed. So we just name it after another famous physicist like we did with the Newton. And we name it the Watt after James Watt. He grew up in a Christian family, Scottish, but later he became more of a deist as his life went on. But he made lots of contributions in physics, especially in the area of heat, and his name will come up again later. So your textbook points out that you have the symbol for watts, which is the capital W, because it's the last name of a person. And you also have capital letter W, which stands for work. Now, obviously, if we were to say work equals force times distance, W here could not possibly mean a watt. It would stand for the quantity called work. But if we were to divide this by time, let's see, and divide this by time, our answer could come out in, let's say, 17 watts of power. So make sure you keep that straight. Now, when we're printing or writing on a test booklet or writing out our homework, we generally don't do italics and non-italics. So you just got to be careful. Of course, W can stand for other things too, like width. And W as an element stands for tungsten. So you got to find the context. Now, the unit of watt therefore replaces a old-fashioned unit of power named for the horse. When they used to have horses doing all the pulling of carts and buggies and things like that, they would talk about your average horse could do this much work in a second. And it turns out that 1 horsepower is about 3/4 of a kilowatt. 1 horsepower is about 3/4 of a kilowatt, about 750. If you need a general benchmark. And that number, of course, you would not have to memorize, but it is a good conversion factor. Now, we don't generally talk about watts because a watt is a very, very small unit of power. If you had a 100-watt light bulb and you left it on for 1 hour, 100 watts is 1/10 of a kilowatt, and a 100-watt light bulb that's been on for an hour would have the power of 1/10 of a kilowatt, because you would take 1/10 of a kilowatt times 1 hour, and that would be 1/10 of a kilowatt hour. And 1/10 of a kilowatt hour is a unit of energy. And let me show you that. So here's my 1 kilowatt hour, which is the reason this is important is because this is how the electric company charges us for electricity. You pay so much money per kilowatt hour. So it depends on how many kilowatts of power an appliance or light bulb is going to use and how long it is on. So 1 kilowatt hour could be a 1,000-watt light bulb, which would be very bright, that's on for 1 hour, or a 100-watt light bulb that's on for 10 hours. That would be a kilowatt hour. And depending upon where you live in the metropolitan St. Louis area, that could be anywhere from about 7 to 12 cents per kilowatt hour. And we're going to have a worksheet on this looking at our appliances later on in late March when we get to our unit on electricity. So a kilowatt is 1,000 watts, and there are 3,600 seconds in 1 hour, 60 times 60. And so a 1 kilowatt hour, and if we remember that that power is work divided by time, or we could say it's energy divided by time. Therefore, energy equals power times time. And here is my power times time. And so 3.6 million joules of energy is the equivalent of 1 kilowatt hour. Here's a rather simple problem. We have a 1,000 kilogram elevator, a metric ton, and it carries a maximum load of 800 kilograms. There's a constant frictional force of 4,000 newtons, and as the cable pulls it upward, and when you're in an elevator, you kind of like friction. What minimum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator car at a constant speed of 3 meters per second? Well, if you've ever been in an elevator, you know that they have a plaque inside that says this elevator is designed to hold a maximum load of so many pounds. And the motor is a motor that has been designed to be able to handle that load and then some. There's always, I don't know what percentage excess they take into consideration, but this motor would be able to more than be capable of handling the maximum load permitted in an elevator, just in case you have people that aren't paying attention to it. So when we look at our force diagram, we've got the weight and the force of friction acting downward because the cable is pulling the elevator upward. And so if you're moving at a constant speed, the force of tension acting up is going to equal the force of friction plus the force of weight of the elevator acting down. And then it becomes a matter of plugging in your numbers. Now, of course, if you're accelerating upward, if the acceleration is 0, the up forces are going to equal down forces. If your acceleration, if it is accelerating, your up forces minus your down forces would equal ma. All right, let's move on to shamu, a killer whale, 32 feet in length, 8 kilograms. They're very quick and agile. They can accelerate up to 30 miles per hour, so I would suggest you not try to outswim it. You better come up with a different strategy, such as prayer, or become very untasteful, bitter. In any case, hopefully you never find yourself in that situation. I doubt I'd be thinking physics at that moment. Disregarding the considerable drag force of water, and that is a big exception or overlook. Calculate the average power of the killer whale shamu if it has a mass of 8,000 kilograms and goes to a speed of 12 meters per second, which is about 27 miles per hour, and it can do that in 6 seconds. So that kinetic energy that it has is going to be 1/2 mv squared, assuming it's just treading water, so to speak. If its initial velocity is 0, like right there, all of the kinetic energy it's going to have is going to be 1/2 its mass times its velocity squared. And then we take that energy and put it right there and divide by 6 seconds, and there's your power. And that's almost 10, let's see, is that 10 to the 4th? 10 to the 4th watts. So about almost 100,000 watts. And that's enough power to run a moderate-sized office building. All right, coming over to this next problem, speedboat power. So we have the average power of this speedboat is it has a mass of 1,000 kilograms. It's going to go from rest to 20 meters per second. So that means its initial velocity is 0. Its final velocity is 20 meters per second. You have a constant drag force. I'm going to call this my force of friction, and we're going to take the drag force into consideration this time. And that drag force is given to us because you'd have to know some hydraulics if you're going to find drag forces, unlike finding friction of one solid like a wheel on another solid like a road. And we have 2 problems. Part B, find an expression for the instantaneous power. So let's look at part A. And the way that I set up the problem, and you're probably used to this now, and you can look at the way they set it up. They have all the positive work on one side and the negative work on the other. I approach it like this. I say, how much energy do I have at the beginning of the problem? What's my bank account of energy? And then when I spend that energy, or use that energy up, where does it go? Some of it goes to overcome the drag of the water, and the rest of it is responsible for the speed of the boat. And so once I articulate my equation, either like this in the book or the way that I like to look at it, and they're related, but it's easier for me to conceptualize it the way I've been doing it. You'll notice that one of the things we need, but aren't given in the problem, is the distance that it takes for the speedboat to go from 0 to its maximum speed. And so we go all the way back to our kinematic equations a couple chapters ago. My final velocity equals acceleration times time plus my initial velocity. And of course, but the initial velocity is 0. So my final velocity is acceleration times time. And I solve this equation for my acceleration. Then once I solve the equation for the acceleration, I drag out my other, pardon the pun, drag out. I pull out my other kinematic equation, final velocity squared minus initial velocity squared equals 2 acceleration times distance. My initial velocity again is 0. And when I plug my numbers in, I see that the distance is going to be 50 meters for this boat. And now I can plug that into the equation up here for D. And I already have my drag force. The drag force was up here, and that's the F sub F. We have my final velocity. Remember, my kinetic energy is 1/2 mass velocity squared. We have both the mass and the velocity given to me in the problem. And so when I plug those numbers in, I can find that the work the engine needs to do is 2.25 times 10 to the 5th joules. And then the last thing I'm going to do is convert it into power by dividing by the time. Put that answer in the numerator, divide by the time, and now I have the power, and then I can convert that into horsepower. And then it says find the symbolic expression for the instantaneous power. And here we're going to have the bigger force, which is the force of energy that the motor can generate, minus the drag force, and is going to equal ma, because the boat is accelerating. And that's the unbalanced force that's creating ma. And then I can simplify that expression. That's not something likely that you will do on a test. All right, energy and power in a vertical jump. So if you're just jumping up and falling back down again, instead of jumping like this, you have your crouch, then you leap in the air where you extend yourself, and then you're in free flight, and then gravity, which has never left the picture, slows you down. You come to a halt at the apex of your jump, and then you come back down again and hopefully land nimbly on 2 feet without injuring yourself. And so the point that we want to make here is that when you look at complex objects like the human body, we look at the center of mass. And typically in a guy, we're using like about the belt, probably be a little bit higher in a guy because guys have broader shoulders. Ladies have broader hips, and so their center of mass is actually a little bit lower than guys. Women are more stable than men, and there's probably a lot of young ladies that would agree with that. That's a joke about some of the craziness of guys, but instability, sorry for that little diversion. In any case, what we're going to do is we're going to be converting all of our kinetic energy into potential energy when we reach the height of our jump. And of course, before you jump, you don't have any potential energy at all, so that's 0. And when you get to the very top, you're no longer traveling upward anymore, so that's 0. So it's basically kinetic energy equals potential energy. And your distance, if you notice the 2 right there, your distance is because you've got this distance when you crouch down, and then you have this distance right here, which is kind of like that distance when you leap up. And so you get twice that distance. One of the things that you will notice, of course, is the masses cancel. So assuming your legs are strong enough, mass is irrelevant here. All right, just as a side note, jumping and exercise are good for you, but not necessarily for losing weight. Obviously, there's a balance sheet going on. You've got your calories in and the calories that you burn if we're using the old-fashioned unit of heat. We'll talk a lot more about that in Chapter 10. Typically, when we talk about diets, we still work in calories instead of joules because we are very old-fashioned and stuck in the mud here in the United States when it comes to the metric system. But in any case, the easiest way to lose weight is to reduce the caloric input. It's really hard to burn off an awful lot of those calories because as you're burning off the calories, you're also generating a tremendous amount of internal energy, which is heat, which is why you sweat. So your muscles are about 25% efficient when it comes to doing work. Now, by the way, a light bulb, the old-fashioned light bulbs, this is an old-fashioned light bulb that had the little filament in it. The old-fashioned light bulbs, before they switched to fluorescent bulbs and from fluorescent bulbs to LEDs, these were actually 60% heat and only 40% light, to show you the inefficiency of light bulbs, which is why a lot of your skyscrapers and large buildings did not need to have any furnaces or heaters in them, because it generated so much heat from all the lights that they were always having to air condition those buildings. Now that when we switch out to the light emitting diodes, which generate practically no heat, now they're finding they've got to figure out a way to get some heat into some of these buildings. All right, just so that you get a sense of the maximum power output from humans over various periods. This little table here shows you that you could probably do 2 horsepower for maybe 6 seconds if you're in shape. You could probably do 1 horsepower, do the kind of work that a horse does in the same amount of time for about a minute. And then, of course, as the amount of horsepower goes down, the amount of time goes up. That would represent how much time you can sustain that much work being done per unit of time. All right, now what about work being done by a varying force? Like when you pull on a spring, you have to pull harder and harder the more you stretch it. It's not a constant force. We usually think of friction as being a constant force as you're coming to a halt. I'm not quite sure that a boat plowing through the water, that the drag force is necessarily constant. I guess a lot depends upon what kind of boat, and certainly you could reach a speed where you're almost skimming over the top of the water and reducing the amount of drag. But a very, very heavy boat, let's say like a cruiser, a cruise liner or an aircraft carrier, you would think that the faster you try to go, the more drag there would be. So I don't know what it would be like for the hydraulics. But imagine we have a situation like this, that we have this much force right here, and then we pull harder and harder, or we push harder and harder, and we get a maximum force, and then we just kind of let up a little bit, and now my force is down to this. And if you look at my y-axis is force, and my x-axis down here is my distance or displacement. And so the slope of my line is going to be my rise over my run, which is the change in y over the change in x. And the change in y is my force that I'm exerting, and the change in x is a distance. And I'll give you a little heads up. That turns out to be the spring constant K. If you remember, F equals negative KD. K is the slope of the line. Now, in this particular case, this is not necessarily a spring. If we actually had a spring, you would have a straight line, and you'd have a constant value of K until you hyperextended the spring, or the elastic, and then it would break. Or it would just no longer go back to its original shape, which means it's no longer pulling back. So in this particular graph, I wouldn't necessarily call the slope of the line K. But if you think about the area under the graph would be the y-axis times the x-axis multiplied by some constant. And I'm going to use, let's use the letter C for constant here, because we're thinking of K as being the spring constant. And so the area under the graph is going to be some constant C times the force times the distance, because y is the force and d is the distance. In other words, the area under the graph represents work times some constant c. And how could we find the area under the curve? Well, one way to find the area under the curve, and we've done this before, is to construct all kinds of boxes, rectangles of equal width. Some rectangles are shorter than others. And you'll notice there's part of each rectangle that isn't under the red line. And there's also parts of each rectangle that should be included because they're under the line, but are not included in the rectangle. And so this is a little bit sloppy, but if we make the width of my boxes smaller and smaller, all of the stuff that I'm not including or shouldn't be including, it gets smaller and smaller, and we approach the actual area underneath this curve. Another way that we could do this would be to, and this is kind of interesting, it's not in the book, would be to cut out a piece of paper that matches this graph. And then put it on a scale and find out how many grams it is. And then get another piece of paper and cut it so that it's a rectangle, and keep trimming this piece of paper until the area here equals the area there. And then and then find its mass. Well, its mass will be, you want to trim this paper until its mass is the same as the mass of the other sheet of paper. Once these two masses, there and there, are the same, then here you just have to take your length times your width to find the area, and that area is the same as that. Kind of a clever way to do it. Or we can use calculus, integral calculus. We can integrate from x1 or x initial to x final over this curve, remembering that dx is similar to delta x here. And as this gets smaller and smaller, I get a more and more precise value. Now, to give you a little bit of an illustration of this, let's come over here and let's look at that spring that we talked about in the last lesson on a horizontal surface. And you have to pull it harder and harder to stretch it more and more, and we're going to get a graph that looks like this. Now, you already know that this is going to be a triangle. And this triangle, the area of the triangle, is going to be 1/2 the base times the height, which equals 1/2 the base, which is the distance, divided by the height, which is the force. And so you can see that my area is the work that is being done, the total work being done when we pull the spring from position 0 all the way to position X. That would be the total work. Or another way we could do it, coming back over to here, is we take the actual equation for force, not for force, excuse me, F here is the function, which would be the equation for the line. And since it's a straight line, remember this was a straight line, it follows the equation y equals mx plus b. And if we have 0 as our origin, b goes to 0, and I'm making this nice and simple, so the equation for my line is mx, y equals mx. So I put mx in as the equation for my line dx. And as you know, when you integrate, your x has a 1 value. So when you integrate, that goes up to x squared, and then you divide by the exponent 2. And notice that this now becomes 1/2 mx squared for the work when you take the integral, which is the equation we learned for the energy or the work being done when you stretch a spring. Because in this case, K is the slope of the line. When we come back up here again, this making sure I did this right, this force times x, I'm sorry, the value of K, I'm losing my train of thought here, it's pretty late. The value of K is going to be the F over the X, which is the spring constant. All right, so here we can do the work required to stretch a spring, and this isn't too difficult. Since it's 1/2 kx squared, we have the spring constant K, and we have the distance of 0.040 meters to this point right there. And then we go to 0.070 meters to this point right there. And the difference between the two is the amount of work in this part of the curve. And I think that finishes the chapter.